Welcome to this lecture. So this lecture is basically on the degenerate perturbation theory. In the earlier lecture, I talk about non-degenerate perturbation theory. Now in this lecture, I will discuss degenerate perturbation theory. So in this, let me write down its title. It is Degenerate Perturbation Theory. Right? So I will talk about this. In the earlier lecture, I talk about non-degenerate perturbation theory. Now I will apply the perturbation theory to determine the energy spectrum using the perturbation theory where some states are degenerate. Right? Degenerate means different state vectors having same energy. Right? So as I discussed earlier, the Hamiltonian of the unperturbed system. So in the similar manner, we will define the Hamiltonian. So let us consider a case where unperturbed Hamiltonian is degenerate that is H naught is the H naught is Hamiltonian and it is a degenerate. And what is the meaning of this H naught is this Hamiltonian and this Hamiltonian is degenerate. What is the meaning of degeneracy? Let me talk about it briefly. Say we are having different states psi 1, psi 2, psi 3. If corresponding to these different states, eigenvalue of energy is same. Say E naught is the eigenvalue of energy corresponding to all these different state vectors. Then I can say that this is a degenerate state. Means, and corresponding to this eigenvalue of energy, there are three different state vectors. So that means it is triply degenerate or threefold degenerate state, right? So let me recapitulate earlier lecture. In the earlier lecture, we have defined Hamiltonian H as psi n is equal to H naught plus HP, and it is also operated with the psi n. It is equal to E n psi n, right? So this is equation number 1. And here this Hamiltonian corresponds to unperturbed system, and this Hamiltonian because of the perturbation when the system is perturbed, right? So let us now choose that. This is from earlier lectures. Now to incorporate degeneracy, let us now choose that E and naught energy level is F-fold degenerate, and it means, and there exists f different eigenstates, and these eigenstates are represented by ket vector phi and alpha, where alpha varies from 1, 2, and so on up to f. So that means if it represents the f-fold degeneracy, that is corresponding to f different eigenstates, there exists one energy level, and let me represent it by E and naught. So what does it mean mathematically? If I try to look at it mathematically, this means that H naught phi and alpha ket is equal to E and naught phi and alpha, where alpha is 1, 2, and so on. It represents up to f, and let me call it as equation number 2. That means, or this equation equivalent to h naught phi and 1 must be equal to E and naught phi and 1. H naught phi and 2 is equal to E and naught phi and 2, and so on. H naught phi and f is equal to E and naught phi and f, right? So this series of f equations is basically equivalent to this equation, right? So this is a short notation for this. And here phi n is a linear combination of phi and alpha. So here the psi n is a linear combination of phi and alpha ket. So that means psi n, it can be represented as summation over alpha varies from 1 to f, and it must be equal to a alpha phi and alpha ket, and let me call it as equation number 2. Also the wave function must be orthonormal, so that means this phi and alpha is orthonormal, means scalar product of phi and alpha with phi and beta, it must be equal to delta function, that means delta alpha beta. Let me call it as equation number 4. Also psi n is also normalized, so if it is normalized, that means psi n it must be equal to 1, and let me call this as equation number 1. So now what should I do? Let me put the value of this psi n from equation number 3. So if I put its value, then it can be represented as psi n it must be equal to summation over alpha, it is a alpha star and phi and alpha, right? This is the value of this bra vector, and let me write down the another bra vector in terms of, say, it's beta. So it is summation over beta, a beta phi and beta, right? So it can be represented like this. So let me simplify this equation. So it simplifies to, it is a summation over alpha beta, and it is A alpha star A beta, and it is phi n alpha phi n beta phi n beta, right? So at alpha is equal to beta, this delta function will become 1, and also the value of this will be, it is a delta function, so it is delta alpha beta. So if I put its values here, then this equation will become alpha beta, and it is A alpha star A beta, and it is delta alpha beta. And if I use this condition here, then this will become simply its value will become 1 for alpha is equal to beta, and this can be written as summation A alpha mod square, right? But its value is 1. So what does it mean? It means that psi n, the scalar product, it must be equal to summation A alpha mod square, and it must be equal to 1. Now using equation 2 and 3 in 1, if I put all these values in the equation number 1, then what will happen? It's summation over alpha en0 or en naught, it is A alpha phi n alpha plus HP A alpha phi n alpha ket. It must be equal to En alpha A alpha, it is phi n alpha, and let me make certain simplification. So now this equation will become, because A alpha is here in this term and it is also sitting with this term, so it can be taken outside. So it is summation over alpha A alpha, it is En0 phi n alpha plus HP phi n alpha, it must be equal to En summation A alpha phi n alpha, right? So this will happen. Now operating both sides with the bra phi and beta. So if I operate with this, then what will happen? Let us have a look at that. So it's a constant, so that means phi and beta can be taken inside it. So what does it mean? Alpha A alpha, it is phi and beta En naught phi and alpha plus phi and beta and HP phi n alpha, right? And similarly, on the other side, it can be written as it is En, it is A alpha, it's a summation over alpha, it is phi and beta and phi and alpha, right? That's what will happen. Now it's a number, it's not a operator because it's eigenvalue and it's an operator. So that means it can be taken outside. So if I take it outside this, then what does it mean? So it means it is alpha, A alpha, it is En naught, phi n beta, phi n alpha, it must, sorry, plus phi n beta, HP, phi n alpha, and it is equal to En A alpha, phi n beta, phi n alpha, right? So that's what will happen. Now, this is basically a delta function. So that means it is delta beta alpha. So if I put its values here, then what will happen is this equation will become summation over alpha, A alpha, En naught, delta alpha beta, plus, you can write down it as delta alpha beta or delta beta alpha, plus phi n beta, HP phi n alpha, it is equal to En summation over alpha, A alpha delta alpha beta. Now let us try to understand these things. As here, if I use the idea that if delta alpha beta is equal to 1 for alpha is equal to beta, and it is equal to 0 for alpha is not equal to beta, so that means if I use this trick here, then rest of the terms will become 0 and it will be remain with the En and A beta only. So that means I can write down this as A beta En, and here and if I use here the idea that alpha is equal to beta, delta function alpha beta will become 1 and it is equal to 0 when alpha is not equal to beta. So that means using same trick here, I can express it as A beta En naught, right? So if I use these ideas here, then this equation will become this equation can be written as this is A beta En naught plus summation, sorry, I missed summation here, it is a summation. So it is summation alpha is equal to 1 to F A alpha phi n beta HP phi n alpha, and it must be equal to A beta E n, right? So if I bring this part towards that side, then this equation will become, this is A beta E n minus E n naught is equal to summation over alpha, and alpha varies from 1 to f. It is A alpha phi n beta HP phi n alpha, and let me call this as En1, and let me call this summation term as in short notation it can be represented as summation over alpha varies from 1 to f. It is A alpha HP beta alpha, right? So I can write down this in this manner. So if I do all these things here and say I incorporate delta function here, so it will become delta alpha beta, and right. So if I use this and replacing this beta by alpha, then this part will become En1, because I have to incorporate summation here, En1 delta alpha beta, and it is A alpha. So if I use these, then these equations can be rewritten as, I can write down it as summation alpha varies from 1 to f, and bringing these towards one side. So it is HP beta alpha minus En1, it is delta alpha beta, and A alpha can be taken outside, and let me call it as equation number 0, and here beta varies from 1 to and so on up to f, right? So that's what we are getting. And what this equation will represent? This equation form a system of F homogeneous equations, and for non-trivial solution, their determinant corresponding to this must be equal to 0, that is HP alpha beta or beta alpha, whatever you want to call, minus En1 delta alpha beta, their determinant must be equal to 0, that is, means if I try to elaborate it, then it can be written as HP11 minus En1 H12 H13 and so on, HP1F and HP21 and HP22 minus En1 and HP23 and so on, HP2F and so on, and it is HPF1 HPF2 and so on. HPF3, sorry, not so on, it's not there, and so on. It is HPFF minus En1, and this determinant must be equal to 0. So that means this is Fth degree equation in En1, and it must have F different roots for En1, right, or En alpha 1, whatever you want to call, because alpha is equal to beta for diagonal terms, right? So that means it must have n roots. So that if n roots, so that means total energy of the system can be written as En alpha must be equal to En0 plus En alpha 1. So that means if it has F values, so if it has F values, so that means total energy will split into F different levels. So in nutshell, I can say that thus F fold degenerate level En0 of unperturbed problem split into F different levels when perturbation is applied, when system is perturbed, right? System is perturbed. So that's all for this lecture, and in the next lecture I will talk about an example of Stark effect of hydrogen atom, where electron is sitting in the second energy level, that is n is equal to 2, and that's a very interesting problem in quantum mechanics. So thanks again for watching this lecture.